So for the fourth day of Brill-Noether's workshop, and for start this day, we have a talk by Jesper Lützen about the history of the function concept of Brill-Noether's account of it. So thanks to accept the invitation, and the floor is yours.
Thank you.
Have, like, if you want question, you can take 1 hour, 10 minutes.
Sure. Fine.
Thanks.
Thank you. Yeah, let me first thank the organizers for inviting me to come here to the Newton Institute. It's a wonderful place to work. Yeah, about half a year ago, I was approached by Karin Schemla, who asked me whether I could give a talk here about something that had something to do with the Brill-Noether report, this one. I was very much surprised because, as I told her, I don't know anything about algebraic functions or algebraic geometry or its history for that matter. But Karin is very persuasive, so asked me to go and look at it again. And so I did, and I realized that at least it started with an introduction with the title, The Concept of Function in Older Mathematics. So I thought, well, perhaps I can talk about that because I know something about the function concept. Because my master's thesis that I wrote many, many years ago was on the development of the concept of function from Euler to Weierstrass. And so I thought, well, okay, I can perhaps say something about this. Because my thesis, which looks like this,
I love the historical document.
Yes. When I was translating parts of it into English for publication, I realized suddenly that Juszkiewicz had just published, while I was translating, published a very nice paper in the archive for the history of exact sciences. And that is sort of the standard version now of this story. And I didn't disagree too much with what Juszkiewicz said, so I stopped translating and just published a small version of it in Danish in Nordisk Matematisk Tidsskrift. What I'm going to do today is to tell this the story that is usually accepted, that is Juszkiewicz's and partly my own version of the story, and compare it with what Brill-Noether says about this. Let me start with the half-a-minute version of the development, starting with, it's actually a sort of process of successful generalizations, starting with the Euler concept of function from Euler's Introductio 1748, in which he defines a function to be an analytic expression or a formula in X. And then 100 years later, we have the so-called Dirichlet concept. I'll call this the Euler concept of function. And about 100 years later, we have what is often called the Dirichlet concept of function. That is, for example, you can find it in Fourier, Dirichlet, and Riemann, saying that a function is a dependence of one variable y upon another variable x, such that for each x there is a unique y. And an expression is not necessarily needed in order to give such a dependence of variables. Well, this story continues and goes on to, for example, generalized functions like distributions, 1945, a generalization of the function concept. Here we have Schwarz. In fact, I have also here filled in a few more details in the story because, in fact, about the same time as Euler published his definition in the Introductio, he became also engaged in a quarrel with D'Alembert about the description of a vibrating string. In that connection, Euler felt forced to admit that you could also have functions defined not by one analytic expression everywhere, but by different analytic expressions in different intervals that he called discontinuous functions. I'll call them Euler discontinuous functions to distinguish them from Cauchy's continuity concept. Well, Euler also himself came up with a new definition in the differential calculus from 1755, where he defines a function as a variable y depending on a variable x. I'll come back to whether that is really a new concept or not. But at least after Euler's death, there was sort of a 50-year period with various definitions of a function. Sometimes Euler's definition was used, sometimes this definition was used. I'll come back to that also. And then after the introduction of the Dirichlet concept, things went on. For example, a number of French mathematicians, Baire, Borel, Lebesgue, asked themselves, but what does it mean to say that for an x there exists a y? I mean, how do you find this y? Do you have to have a constructive way of doing it or what? So there's a discussion about that. And then in partial answer to that, Bourbaki came out with the definition of a function as a map from A to B, or rather as a subset of A cross B. And I'm going to talk only about this story going from Euler to the Dirichlet concept. This had a huge impact on the mathematical practice of the time, whereas the later developments here, well, not this distribution also had an impact on the practice of mathematics, but these three, they're more like sort of logical hygiene, I could say, and had very little, as far as I can tell, impact on how working mathematicians worked with functions. So let's turn to Brill-Noether. Here I had thought I would give a description of their work as historians of mathematics, but I don't need to, because we have already on Tuesday heard Mireia give a talk about that. So I will skip these, except, wait. This one, I want to quote my favorite Whiggish statement from Brill-Noether, where they say, referring back to Zeuthen, they say that he, meaning Apollonius, expresses the equation of the conic sections in a geometric form that replaces the modern algebraic sign language. That's beautiful, isn't it? Well, but so let me go directly to the question, does Brill-Noether's account of the function concept, the history of the function concept, does that, is that the same as the one I've just given, or is it different? And in order to do that, I will point to a particularly a strange statement by Brill-Noether. And in order to do that, I'll just have to say a little more about the introduction of the function concept, because Euler wasn't, in fact, the first one. You can go all the way back, at least, to Sharaf al-Din Artusi to find something that looks like functions. Also, James Gregory has a definition in his Vera Circuli et Hyperbolae Quadratura, where he talks about a quantity composed of other quantities through any number of imaginable operations. These two are not mentioned by Brill-Noether, they probably didn't know them, but they do refer to Leibniz's use of the word function. He's probably the first one to use that in this sense. And for Leibniz, a function is a geometric quantity depending on the point on a curve, such as an abscissa or ordinate or subtangent or radius of curvature or something like that. So it's a geometric concept here. But that was then changed by his student, or yeah, I don't know what we should call him, follower, Johann Bernoulli, who says that a function of a variable quantity, he means a quantity composed in any way of this variable quantity and constants. So here it begins to have sort of an analytic meaning, and that was made even clearer by Euler, who rephrased his teacher's definition as follows in the Introductio: a function of a variable quantity is an analytic expression which is composed in any way of this variable and constants. So these are almost the same definitions, these two, the Bernoulli and the Euler definition, and that is also remarked by Brill-Noether. Now, what I wanted to point to here is then what Brill-Noether continues to say about this. So after the introduction of analytic geometry and differential calculus, they write, soon most problems deal with the concept of the dependence of one quantity upon another. the Leibnizian word function obtains citizenship, meaning in mathematics, and with Johann Bernoulli, its present-day meaning. This is really strange, right? Because that is not in accordance with the story I just gave you before, in which the Dirichlet principle, Dirichlet's function concept was certainly the most widely accepted at the time where Brill-Noether wrote their report. So how do we explain this? And Brill-Noether, of course, knew this. They also talk about the Dirichlet concept. So why do they write that way? Well, I think the reason is that they have a different purpose for their discussion of the development of the function concept that I and Yuskevich have had, where Yuskevich and I would tell about a story about a concept that is sort of expanding, starting with the analytic expressions of Euler and then being generalized to the Dirichlet concept and perhaps even to distributions or something like that. So it's a generalization process, whereas Brill-Noether, they're actually only interested in algebraic functions, and they can in a certain way be said to be lying inside Euler's analytic expressions. It's just a part of the analytic expressions, and they are more interested in finding these subsets of the analytic expressions, in particular the algebraic functions here. For that matter, I mean, Euler's, or the Bernoulli concept, is sufficient, whereas Leibniz is not sufficient. So it doesn't have the present-day meaning with Leibniz, but it does, for them at least, with the Euler concept. That's sufficient for them. So what is the story they tell about the development of the concept of an algebraic function? Well, let me take a few steps on the way they take us. They say that the idea goes back to Descartes' distinction between geometric or mechanic curves, or algebraic and transcendental curves. And he also says that, they also say that Descartes introduced the higher algebraic curves. The quadratic curves had been introduced by Apollonius or the Greeks, but with Descartes we get also the higher curves. But only Newton, they say, understood the concept of an algebraic function without formulating it explicitly, showing how one can express the root of an algebraic equation whose coefficients are rational functions of a variable as a series in the increasing or decreasing powers of this variable. So Newton was the first one who sort of understood the idea of an algebraic function, although he didn't have a proper definition. Then Euler has a definition. He defines an algebraic function as an analytic expression which is expressed by using only the rational operations and the extraction of nth roots. Gregory has had a similar concept of an analytic composition, he calls it. And Euler also allows implicit functions defined as solutions of algebraic equations. So implicitly given functions are also allowed according to Euler. But it's according to Brill-Noether, Abel, who is the great hero of the story here, because he's the one who gives the first correct definition of an algebraic function, saying if we have a polynomial in x and y, then we can describe a function y of f of x by plugging in an x, solving for y, and that will give us y equal to f of x. But not only does he have the correct definition, he also, they say that this concept of algebraic function is here for the first time included in the area of a theorem. Here they are referring to Abel's theorem about abelian functions. It thus receives life and meaning. In this sense, Abel is the founder of the theory of algebraic functions. I find it quite interesting to see here that Brill-Noether, they know that in order to describe the development of a concept, the historical development of a concept, it's not enough to look at the definition of that concept. You have to look at how it's used. And they say, well, not only did he have the correct definition, but he also used it in a way that sort of gives him the priority here. Now, about the Dirichlet concept of function, I'll come back to what they say about it. They do say something about it, but not very much, Brill-Noether. And you can say, why did they discuss it at all? because if they're only interested in algebraic functions, then they don't really need the Dirichlet concept. But of course, I mean, they knew that at that time it was the almost universally accepted modern concept about 1890. And secondly, and I think more importantly, one of the major actors in Brill-Noether's report was a strong supporter of the Dirichlet function concept, namely Riemann. So they have to discuss Riemann, and so they have to introduce this new concept. But it's also quite clear that they didn't like the Dirichlet concept. They thought it was unnecessarily complicated. In order to show you that, let me just, you can already see that when they discuss Descartes. They say about Descartes here, the distinction between algebraic and transcendental curves goes back to Descartes. When Leibniz criticizes him for excluding the latter, that is the transcendental curves, from his geometry, the present state of science seems to justify this self-restraint rather than to refute it. So according to Brill-Noether, Descartes was right. One should exclude transcendental functions, because that's what you see here. It justifies the self-restraint by Descartes. So they think it's okay to leave transcendental functions out of the question, and they get even more sort of outspoken when they discuss Riemann. Of course, they quote Riemann when he talks about the Dirichlet concept and say that his functions are not supposed to be given by an analytic expression. And they also say about it they praise Riemann for his intuitive richness of thought. But they call this use of the general concept of function, they call it fluid. And that's not meant as a positive thing to say about the concept. Yeah, I think so. Oh, is it? Well, maybe I.
No, but it's interesting because.
We can discuss.
Yeah, that is. Sorry. But then they say about Riemann here. They criticize his approach for being unrigorous, and of course they could criticize the Dirichlet principle, which was usual at the time after Weierstrass had pointed out that there's a confusion of minimum and infimum in that one. But they sort of point the finger particularly at the concept of function here. They say, but the goal was too high, Riemann's goal was too high, and the foundation for its construction not secure enough. The use of Dirichlet's principle in the generality required by Riemann is, as one has now realized, subject to considerable concern, which is directed against operating with functions defined in the indefinite way used by Riemann. The function concept in this generality, incomprehensible and evaporating as it might be, does not allow controllable conclusions. I mean, I may have completely misunderstood this passage, but I think this is a criticism of the Dirichlet concept of function. And they actually argue that since they consider Riemann's main goal is to make a theory of abelian functions, abelian integrals, he should have limited himself just to the analytic expressions. There was no reason to expand it to the Dirichlet functions. And in this criticism, he was not alone, because according to Hurwitz, and here I hope I'll quote correctly, that Weierstrass should have said that the Dirichlet function concept is in general completely unsuitable and unfruitful. In fact, it's impossible to derive any general properties of the function from it. So they were not alone in this criticism. There's another way in which the stories that Juszkiewicz and I tell differs from Brill-Noether's, namely that, especially I would think one should emphasize applications quite a lot in this story, whereas Brill-Noether tries to downplay it. They do mention applications. I've written some here. The only one they go into some detail with is Riemann's use of the ideas from potential theory and electrostatics in his use of or arguments for the Dirichlet principle. But otherwise, they don't really go into the applications. They sometimes just say there are some applications here. We won't discuss it. That's often the way he handles it. And in some cases, I have the impression he more or less says that applications are mostly there as an excuse for doing research in pure mathematics. That's, for example, how I think he deals with Cauchy's use of the calcul de limite in astronomy. He says, well, yeah, these, but I mean, he's mostly interested in the mathematics. And he even cites Euler, quite applied mathematician, to say that pure mathematics is suited to extend the limits of analysis and to exercise the powers of our mind. A quote that resembles quotes by Jacobi and others at this time, showing that they were, as far as I can see, they worked in the style of these neo-humanist German mathematicians at the time. Okay, so let's go into the text and this introductory chapter, which is called The Concept of Functions in the Older Mathematics. However you, I don't know how you translate that, but it's not, there's no simple translation of that word. Anyway, this is a prehistory because it's the story of the concept of function before there was a concept of function. So it's the roots of the notion of function they are looking at here. And that, of course, is slippery. We know that. It's difficult to do that without sort of falling into a Whiggish trap here. And in this case, it's even worse because the question of finding the roots of the concept, you can ask, what concept are we talking about? Are we talking about the Euler concept, the expressions? Are we talking about the Dirichlet? Are we talking about the Bourbaki? Which concept is it we're looking for the roots of? And when you start, actually, the opening words of that report says, the idea of the lawful dependence of a quantity upon another is so old as mathematics itself. That looks great. It looks like the Dirichlet concept, right? But then you look into what they say about this back in time. And well, I thought, well, then they'll begin to discuss very simple functions like multiplication tables or reciprocal tables or Egyptian tables of 2 over n, or even more, of course, such Ptolemaic chord tables or something like that. But there's nothing of the kind. What he does instead, he goes directly for continuous variability, and he quotes Seuden in particular for the discovery that the Greeks had such a thing, and they discuss loci problems, geometric descriptions of curves, which is described by some geometric property. And they discuss this implicit idea of variable you will find in this discussion of loci, but they don't mention the obvious transcendental ones like Archimedes' spiral or the quadratrix or so. No, they go directly for the Apollonian conic sections and says, well, their symptoma has then been translated by Descartes into quadratic equations. And at this point, they point to algebraic symbolism, in particular with Diophantus and in particular with Viet, which allows a general algebraic expression. Then you are able to write down a general algebraic expression by way of this notation. And this was then connected up with geometry by Fermat and Descartes in their analytic geometry. So you see how he can wind a beautiful thread going from ancient Greece up to today, which lands exactly where they wanted to land, namely at the algebraic functions. So that was the prehistory. Now let's turn to the history. What do they say about Euler? First of all, they say that Leibniz's and Bernoulli's definitions didn't have much consequence generally, but Euler's did. And they say with Euler, the word function was made familiar to the scientific world. His merit lay not in the introduction of the word, but in the recognition by the Leibnizian school that one need to collect the many dependency relations that one had met, the rational, the irrational, and the transcendental, in one concept. Thanks to the sign f of x that Lagrange later gave citizenship in mathematics, it now dominates all the disciplines of pure and applied mathematics and has lent its name to a special branch of science, the theory of functions. Now, before I continue with this, I want to pick on one particular thing that I thought was completely wrong when I read it first, namely this attribution of the symbol f of x to Lagrange. Because, in fact, if you, in Cajori, you can see that you can already find it in Euler's, in a paper from 1734. That's way before the Introductio. And also, Brill-Noether does admit that you can find it in connection with the solution of the vibrating string that Euler and D'Alembert writes in this form here. So is Brill-Noether completely wrong? No, really not. Because I thought, let me look into the Introductio and find all these f of x's that I expected to find there. I couldn't find one. I couldn't find any f of x there. Whereas if you go to the Théorie analytique, Théorie des fonctions analytiques, there are many f of x's. I have here, can show you a picture of Lagrange in front of a blackboard with his famous theorem saying that any function can be expanded in a power series. And there you do find, and it's taken from the Théorie des fonctions analytiques, you see it says f of x plus I is equal to, but then it says fx plus pi. Now, there's no parentheses here. And here there's not even an x. This p is a function of x. That's the one he calls f prime. By definition is this p here, but there's not even an x. So it's not a standard way of writing functions at Lagrange's time, but it is probably from him that we have gradually developed our way of writing functions like f of x. I think the reason why there is a parenthesis here is that we take it on the value x plus I. So I think that's why the parenthesis is there. So I think actually here I learned something. Somebody asked, what can we learn from this by reading it again? That's one thing, when I saw it, I thought it was wrong, but I think they're actually right. The notation f of x was made popular by Lagrange. So what are the big changes that the introduction of the function concept gave to mathematics? That is a question I think it's interesting to ask, but in fact, if you look in Brill-Noether, they hardly discuss it. But from the usual modern story, we learn that there are at least two ways in which it changed analysis. One is that degeometrization. If you look in L'Hôpital's textbook, it is an analysis of the infinitely small for the understanding of curves, for the study of curves. It's curves we're studying, it's geometry we're studying here. Whereas with Euler, analysis came to be a study of functions. It's a purely analytical study. Well, then it can be applied to geometry, and that's what he does in the second volume of the Introductio. But an analysis as such, differential calculus as such, is about functions. It's not about geometry any longer. And this is also the same development we see in connection with mechanics. I mean, Newton described mechanics in sort of synthetic Euclidean terms, but Euler says about himself that already when he was young, I have as far as possible attempted to extract the analysis from the synthetic method. So he also did that in mechanics, and it's of course well known how Lagrange in his Mécanique analytique in the preface says, one will not find any figures in this work. And he's very proud to have made mechanics a part of analysis. So this degeometrization is one thing that happened. Another one is the the different kind of variables that enter into analysis. If you write an equation like this for a curve, well, then x and y play exactly the same role. They are on the same level. But if you do it by way of a function like this, well, then you have x is the independent variable, y is the dependent variable, and they play different roles in this game. So what does that matter? Well, as Henk Bosch has pointed out, especially when we talk about handling infinitesimals of second order, it makes a huge difference. Because if we look at a curve given by a function like this, then we assume that d dx is 0, that dx is given as a constant infinitesimal. Whereas if we just have x and y playing the same roles in the equation, well, then we have to sort of choose whether we want d dx to be 0 or dx to be a constant or dy to be a constant, or we just want both of them to be able to vary. And in the last case, there are 3 different formulas, for example, for the curvature of a curve. So the function approach, you can say, corresponds to a choice of dx to be constant, or Newton's choice x prime x dot equal to 1, that is taking x as the time variable. So did I say that right? Okay. So this is also a change in mathematical practice coming out of the introduction of the function concept. The distinction may be not as big as Henk Bosch might make it sound, because in fact Euler does allow functions that are given implicitly. For example, this equation here, according to Euler, gives us capital Z as a function of small z, even though we don't know the solution of the 7th degree equation here. It also shows that functions according to Euler, especially these algebraic ones, can be multiple valued. There are 7 values of z here. If we make it a complex, if we accept complex values, and Euler does that. Now, let me just say a few words about the fundamental concept of the fundamental theorem of algebra in this connection. Because here, Brill-Noether, they attribute the formulation of the fundamental theorem of algebra to Girard and Descartes, and they attribute the proof to Gauss. Well, modern historiography agrees, but there's one complication here, namely that Girard and Descartes' fundamental theorem of algebra is not the same as Descartes'. And because Descartes and Girard, they say that an nth degree equation has n imagined roots. But they did not claim that they were all necessarily of the form a plus ib, a plus square root of minus 1 times b. And in fact, Leibniz gave an example where he thought that was not the case. This 4th degree equation, if you factorize, you will see that it contains roots of the form square root of the square root of minus 1. And Leibniz didn't know that they could be expressed as complex numbers. So he thought this was a higher kind of algebraic complex number. And he thought there was sort of a whole hierarchy of complex numbers. Then Nicolaus Bernoulli showed that you can actually factorize it in a different way. And these two, of course, these two real quadratic factors, they of course have complex roots. So they say, no, all the roots are actually complex. And that convinced both Euler and D'Alembert that the standard version is correct, namely that an nth degree equation has n complex roots. And they even tried to prove it with proofs that were then not accepted at the time, and Gauss gave the now accepted proof. About the complex numbers, we have already heard this quote, but on Tuesday. But let me just repeat it. Brill-Noether say the imaginary branches of the curves were not available for Newton and the following century. Nobody dared attributing complex values to the indefinite coefficients in an equation or a series expansion until Gauss and Cauchy had awarded citizenship to the complex numbers in analysis. Well, that is probably true when you talk about the application to curves. But in his analysis as such, Euler certainly accepted complex variables. And of course, that's the reason why he could prove these wonderful Euler theorems that connects the trigonometric series and the exponential functions. And that leads me to an observation about Euler's concept of function that I find extremely important, namely his view of variables. Remember, a function is an analytic expression in a variable x. So what does a variable mean? And according to Euler, a variable quantity is an indeterminate or general quantity that in itself contains all values without exception. Thus, a variable quantity includes all imaginable numbers, the positive and the negative, the integers and the fractional, the rational and the irrational and transcendental, even zero, and the imaginary numbers are not excluded. So zero is particularly strange, apparently. So, expressed in a sort of ahistorical modern way, all functions are defined everywhere. We can plug in the x, and the x can be anything, any number. How serious did he really take that? I mean, can that really be true, that he thought that was the case? Yes, it is true. And we can see that from Euler's involvement in a controversy between Johann Bernoulli and Leibniz concerning the value of the logarithm of x for negative values of x. It was a debate that had taken place in 1712 to 13, a correspondence between Leibniz and Bernoulli. And Euler then commented on it in a paper from 1749. Now, one thing I think is interesting is that they don't agree upon the value, but they agree upon one thing, namely that it makes sense to ask the question, what is the logarithm of a negative number, even though you have only defined it for positive numbers? So somehow there is a value there. Now, so Bernoulli had given an argument showing that log x is equal to log minus x. He says d log x is equal to dx over x. Therefore, d log minus x is d minus x over minus x. So that is also dx over x. So d log x is equal to d log minus x, and integrating, we can get that log x is equal to log minus x. Well, so that Leibniz said, no, that's not valid. Of course, what he should have said is, you have missed a constant here. But that he doesn't point that out. He says, no, it could be that the rule of differentiation of the logarithm can only apply to positive x's. So the argument is not valid. To that, Euler said, no. But one must admit that this objection is not only very weak, since it's not supported by any valid reason, but that it completely upsets the differential calculus of logarithms. Indeed, since the calculus operates on a variable quantity, that is, on quantities considered in general, if it was not true in general that d log x is equal to dx over x, whichever quantity one gives to x, be they positive or negative or even imaginary, one would never be able to use this rule, the truth of the calculus being based on the generality of its rules. So he actually believes not only is x here going to be any complex number, but all the rules, differentiation rules and so on, they are universal. They have to work everywhere, because if they don't work everywhere, then they don't work at all. I think this is very important in order to understand Euler's idea of a function. You can see similar things when he, for example, calculates this by long division. You will get this power series. And in his opinion, this equality sign in some formal sense holds, even though this right-hand side doesn't converge. Although they don't, of course, then in that case, you can get things like -1 equal to this sum here, which numerically doesn't make any sense. But in some formal way, it does make sense to Euler. Well, that idea of the generality of analysis was questioned again by Euler himself in connection with the discussion of the vibrating string. It started with this paper here by D'Alembert from 1747, where D'Alembert started out deriving the wave equation. This is a slightly modernized way of writing it. And he found the general solution to it, where it's this one, where psi and gamma are arbitrary functions, he says. Well, Euler then wrote a paper which is actually much clearer than D'Alembert's, and he and D'Alembert then began to discuss the initial value problem. Oh, here we have the formula for the general solution down here. So they begin to discuss the question, if we have a musical string, so a guitar string, it's fixed at 2 points at distance L, and then we give it a certain shape, and then at time 0 we let go and see how does it vibrate. And it's easy to see that in that case the general solution will have this form here, where f is the original function here, and it has to be an odd function, and it has to be periodic with period 2L. Now, of course, if this function its analytic expression is of this kind, well, then we just prolong it and find those values of f we need to use here. But if it's not, well, then Euler says, well, then you, instead of taking this prolongation here, this extension of the function for other values as x, then you instead you take this function and you turn it upside down and it does like this, and then you have an odd function. And then you just prolong it by continuing it periodically with period 2L. And then we have this, and that's the function we need to use up here. So D'Alembert answers, no, this doesn't work. If f is not odd and periodic, that means if the analytic expression for f in this interval is not periodic and odd, then this is not allowed, because differential calculus is valid for functions, that is for analytic expressions. And this one, Euler's continuation, is not an analytic expression. It's different analytic expressions and different intervals, and analysis doesn't work then. Well, Euler says, no, actually, I think it does. And physics actually forces us now to extend analysis, so it includes these new mixed functions, as he sometimes calls them, functions that have different expressions in different intervals. And he even notices that if we want to describe say a plucked string, then you will even have that the initial value function will have two different expressions, a linear expression here and another one here. So he wants to include these, what he calls discontinuous functions, that are given by several analytic expressions in different intervals. And he even says that the equation may even change from point to point, corresponding to any hand-drawn curve. So even though it's just the value at a point and you want to find one more value, one y value, he still, for some reason, needs the expression. He says the expression may change from point to point. It's, he continues to have this expression in there. And D'Alembert then answers, well, but the differential equation is actually not satisfied in that case, and they have their discussing back and forth, and the discussion isn't settled in the 18th century at all. And it becomes even more muddled when Daniel Bernoulli entered the scene and says, well, I don't understand what you are talking about here. As far as I can see, the only thing I can understand is that harmonic oscillations, that string has to be described by a superposition of harmonic oscillations. So you have the ground tone here, you have the octave here, and so on, and you superpose these, and then you get the vibrating string and its shape. And to that, Euler and D'Alembert says, well, yeah, that's true. That is a possibility. But there are many functions that cannot be expressed in this way. For example, says Euler, if you have a polynomial, start with a polynomial, a polynomial is never periodic and therefore cannot be used, cannot be expanded in such a sinus in a trigonometric series. I mean, here Euler is obviously sort of caught in the crossfire between his two allegiances, namely the one, an allegiance to the generality of analysis, which he really deeply down believes in. And then on the other hand, he also believes that mathematics should be applied to physics. And so he wants to get both, and some of his arguments are really modeled in this place. Quite clear, he doesn't quite understand how to go about this new function concept. He also points out that although this new function concept of the Euler discontinuous functions have come in connection with a very specific physical problem, they actually belong quite naturally in the calculus, especially when it comes to partial differential equations. Let's take the simplest example that he mentions in his paper on the use of discontinuous functions in analysis, but it's also mentioned in his 3-volume work on integral calculus. So the simplest partial differential equation, we have a z, which is a function of x and y, and we want to solve this partial differential equation. Then, of course, if y is just constant, we can solve it and we get this ax plus a constant, a linear function here. And then Euler says, well, but this constant is different from different values of y. And for varying y, the constant can denote an arbitrary function of y. And therefore, the solution is this one, where f here doesn't need to be an analytic expression. It can be one of these arbitrary functions. And this is how they get into analysis according to Euler, these functions. He himself says in a letter from 1765 that analysis as it has been treated until now can only be applied to curves whose nature can be included in an analytic expression. But the controversy of the vibrating string opens to us a new career in analysis by making us capable of applying the calculus to curves that are not subject to any law of continuity. Now, it's hard to say exactly what Euler had in mind here. Did he just have in mind that, that you can include these general functions when you integrate partial differential equations? Is it just they belong in this little corner up here in analysis where we integrate partial differential equations? Or does he mean that you have to find a completely different approach to analysis that allows these general functions from the start? And it's not, well, I think you can say what he did was this, he did show that they belonged in the solution of partial differential equations, but he didn't change his way of dealing with functions in other ways. And for example, in his differential equations, in his differential calculus, in the integral calculus, except for this partial differential business here, functions are just what they were in the introductio. So he doesn't really change his habits about functions, except for this little corner up there. Now, this story is made more complicated by the fact that Euler, in his differential calculus, wrote a new definition of function, namely, when x means a variable quantity, then all quantities that depend in some way on x or is determined by it are called functions of x. Now, this, of course, doesn't mention analytic expressions explicitly, and Yuskevich and others have said that this is the same as the Dirichlet concept, and therefore the modern concept should be called the Euler concept. Well, Euler concept 2 or something. Well, I'm a little hesitant to follow Yuskevich at this point. There's no example in the differential calculus of functions that are not given by analytic expressions. And it is used exactly as he used it in the introductio, and he borrows all the results from the introductio into this differential calculus. Differential calculus is built on the results from the introductio. And what is even more strange is, I mean, this new definition came in the middle of the discussion with D'Alembert about the vibrating string. But in this discussion, he never refers to this new definition of function. He continues to talk about analytic expressions all the time, that they can change from point to point, for example. I mean, if he had really absorbed the idea of the Dirichlet concept, he wouldn't have said that to an x there is an analytic expression. No, he would say to an x there is a y. But he doesn't say that. And so it's very strange that he doesn't appeal to this new function concept. And so I think it's fair to ask these two questions. Did Euler really notice the difference between his introductory definition and the 1755 definition? And also, did Euler see the relation between his discontinuous functions and his new 1755 definition? I must say I hesitate to say yes. I think the answer is no. But I disagree with many other historians. Now, this question about partial differential equations and the arbitrary functions coming out of those got a life of its own. 4 years after Euler's death, the Academy in St. Petersburg formulated a prize problem. Do the arbitrary functions introduced when partial differential equations are integrated belong to any curve or surfaces, either algebraic, transcendental, or mechanical, either discontinuous or produced by a simple movement of the hand? Or should they legitimately be applied only to continuous curves susceptible of being expressed by algebraic or transcendental equations? And to this, Arbogast, who won the prize, he answered, functions, these arbitrary functions, they can be both discontinuous in Euler's sense, but they can also have jumps. So they can also be discontinuous in Cauchy's in Cauchy's sense of the continuity. Here he slightly disagreed with earlier writers like Condorcet and Laplace and Abbé de Camusot, who had concluded that these kind of arbitrary functions, they can be Euler discontinuous, but must be, Euler Cauchy continuous. But at least there was some discussion. Sorry. Oh, let's see what I can do. Waving my hands too much. Okay. So this discussion continued after Euler, but in general, there was a period here after Euler's death where the concept of function was treated sort of in various ways or defined in various ways in different treatises. So many just repeated Euler's definition, and some definitions sounds more general, like, for example, in Lacroix's famous textbook from 1797, where he says that every quantity whose value depend upon one or more other quantities are said to be a function of the latter, whether one knows or one does not know by which operations one passed from the latter to the former. Well, that sounds very much like the Dirichlet concept of function, until you read a couple of lines below, where the only example that's given is the solution of a quintic equation as a function of its coefficients, which is, well, it's just Euler's implicitly given functions he's mentioning. So probably he doesn't think of this as a more general definition. And you find a similar situation in Lagrange, in his Théorie des fonctions analytiques. He says first that a function is a y depending following a given law, depending on x following a given law. Oh, okay, that sounds perhaps a little more general. But again, if you go further a couple of pages, then he rephrases this and says that a function of one of several variables are all expressions of calculation in which the quantities enters and so on. So there we are back to the Euler concept immediately. So you have a period where this goes on, and then, yeah. Oh, I should also mention Cauchy here. Cauchy, where do I have Bruno? I put this picture for you. Well, it is Cauchy, it's his brother, right?
I think it's
That's what you say, at least.
in the family. No. I said, no, I don't know what.
Anyway, I've taken this from the French. I've taken this from the French edition of Wikipedia. In the English one, it is a picture of the real Cauchy. What?
Sorry, no, it's another in my book.
Yeah.
The first edition.
Yeah.
There is a picture.
I know.
Of Cauchy, which is wrong because it's a brother's portrait. But in fact, it's not this.
Oh, that's not that one. Oh, so even I.
This one, I don't know. It appears.
Maybe it's okay. So that's not his brother. Okay. It's at least it's taken from Wikipedia, but only the French edition. The English edition has a correct picture of Cauchy.
Because I published a portrait of Cauchy in the first edition, and somebody in the family of Cauchy told me, no, it's not true, it's not Cauchy.
Okay, anyway, what I really wanted to do was to tell you how he defines a function in the Cours d'analyse. He again talks about quantities that are related to each other and so on, but very quickly he talks about the one being expressed in terms of the other. So he also have expressions here. So again, it's not so obvious what his definition covers. But this is the right Cauchy. As he famously said sorry, I should go one. Because there is one way in which it's different from Euler's, namely when it comes to the definition of a variable quantity. Because according to Cauchy, a variable quantity we call a quantity variable if it can be considered as being able to take on successively many different values, but not all values. So this is sort of part, this step here is a part of his criticism of Euler's belief in the generality of analysis or algebra, as he says. And he says it very famously in the introduction here. As for methods, I have thought to give them all the rigor which one demands from geometry, so that one needs never to rely on arguments drawn from the generality of algebra. So this is a direct criticism of Euler. And he says that such arguments we must also observe that these kind of arguments, tend to grant a limitless scope to algebraic formulas, whereas in reality most of these formulas are valid under certain conditions or for certain values of the quantities involved. So here he's quite differently not following Euler. And in particular, as he talks about it later on, he insists that a divergent series has no sum, and also that if you have a function that's defined for the real numbers, you cannot just plug in a complex value. You have to first tell by a definition what it means before you can do that. This I'll drop because I don't have the time. There are some inconsistencies in the way Brill-Noether talks about Cauchy, but never mind, we'll drop them because they don't have anything to do with the concept of function. Now, what do Brill-Noether then say about the Dirichlet concept of function? Well, here's more or less what they say. The applied disciplines, mechanics and physics, were led to use the word function also for such dependency relations that does not immediately allow an explicit expression of the dependent variable in terms of the independent variable. The properties of the Fourier series allowed a means of giving such expression afterwards. So actually, he doesn't discuss the debate about the vibrating string at all, or Euler discontinuous functions. They're not mentioned as far as I can see. They don't discuss in what way mechanics and physics led to this new function concept. It's interesting also that this new concept of function only applies in the applied disciplines, apparently. It's the applied disciplines that have this new function concept. It's as though it belongs over there with the applications. Okay. So let me say a few words about the introduction of the Dirichlet concept of function, a little more than Brill-Noether says. it actually is in connection with the question of heat conduction that Fourier studied in various manuscripts from the beginning of the 19th century, and that was published then in 1822. So he's talking about heat conduction in various solid bodies, and for various bodies he's then integrating this differential equation that he sets up, the heat equation, and he integrates them by using this method of a separation of variables. It is probably the first, or it is the first case where this method is used in all its generality. In this connection, he comes up with the question, a given function f of x, can it be expanded in a trigonometric series like this? Similar to what Daniel Bernoulli had asked about the vibrating string. In this case, Fourier actually was able to say that if f of x is written as such a trigonometric series, then the coefficients here, a and b, they are described by these integrals here, the Fourier coefficients. And then he tries to prove that if we then take these and plug it into this sum here, then this Fourier series will actually converge to f of x. The latter is really not very rigorous, his proof, but that's what he tries to do. And in this connection, f here, the function that we expand in power series, that represents sort of the initial temperature distribution along an edge of this body. And of course, there's no reason to believe that that should be given by an analytic expression. Just as in the case of the vibrating string, there's no particular reason why the initial shape should be given by an analytic expression. And so, as in Euler's case, Fourier then generalizes the concept of function and gives it this formulation. In general, the function f of x represents a succession of values or ordinates, each of which is arbitrary. An infinity of values being given to the abscissa x, there is an equal number of ordinates f of x. All have actual numerical values, either positive, negative, or zeros. One need not assume these ordinates to be subject to a common law. They succeed each other in any manner whatsoever, and each of them is given as it were a single quantity. Now, this is really new. It's also interesting to see that he notices that having given such a new definition of a function, he also has to adjust the other concepts in analysis, in particular the integral. Because what does these Fourier integral mean when you have the function f given by such a thing? I mean, the Euler way of finding the integral is to find its antiderivative. But how do you find antiderivatives of these things here? So instead he says, well, we define the integral simply as the area under the curve. Of course, Cauchy, almost at the same time, did much better in his courte analyse. But at least it's interesting to see how he tries to adapt the new function concept by changing some of the fundamental ideas, some of the fundamental notions of differential calculus. Dirichlet was a student of Fourier, and he was the one who gave the first rigorous proof of convergence of the Fourier series of a large class of functions, piecewise monotonous, piecewise continuous functions. He published it in two papers, 1829 and 1837. In the first one, there's no definition of functions. In the second one, there is the following one. He's looking at an interval, and then he says, if each x corresponds to a single y, finite y, such that when x runs continuously through the interval from a to b, then y equal to f of x will simultaneously vary gradually, then y is called a continuous function of x in its interval. So apparently he's just defining a continuous function here, but there's this extra addition here. Here it's not necessary that y depends on x according to the same law in the entire interval. One does not even need to think of a dependence that can be expressed through mathematical operations. So this is the reason why Hankel called this the Dirichlet concept of function, as I've also done in my talk here. You can say, well, is that really correct? Because in fact, he only defines a continuous function. But of course, we can just leave out those few lines here, and then we have a description of a general function. And also, actually, he gave examples of discontinuous functions. In particular, this one, the Dirichlet function, which is one constant for x rational and another constant for x irrational. It's probably the first time a function is given without any reference to an analytic expression. And for that alone, I think it's okay to call it the Dirichlet concept of function. But I think there's another reason for that, namely that he's the first one who applies the new concept of function in a constructive way. I mean, in general, you can say if you extend the concept of function, then proofs get more complicated. But some proofs get simpler. And the first example of that, I think, is this proof of the convergence of Fourier series given by Dirichlet. And the main lemma in that paper is the following. If f of x is continuous and monotonic on the interval from a to b, which is a sub-interval of the interval from 0 to pi half, then this integral here converges to 0 for n tending to infinity, except when a is equal to 0. And in that case, it converges to pi half f of 0. Now, he proves it by first looking at the case a equal to 0. So we have a function. So we have a function here on this interval from a to b, and it's somehow, I don't know, monotonous. It should be monotonous. So like that, and then we actually look at the case where a is equal to 0 first, and the proof of that is a masterpiece in rigorous mathematics. It's probably the first really complicated proof in analysis that is done with all the rigor we can require even today. It's amazing, wonderful proof. So he does that first, and then he says, let's now look at the case where a is equal to 0. Well, he says, well, we can actually rework that from the previous example by just continuing this function in a way which is continuous. So it starts here, and then it's also monotonous. So it goes like this somehow. Then we get a new function from the interval here. Let's call it f1. But that satisfies now all the requirements for the case of a equal to 0. So that means that the integral from 0 to b and from 0 to a of this f1 function here converges to pi half over of f of 0. And therefore, the integral from a to b of f, which is the same as the integral from a to b of f1, because they're the same here, that converges to, well, pi half f of 0 minus pi half f of 0. So it converges to 0. It's beautiful. It's beautiful. And you see how he here uses this idea that if you have given the function on this interval, well, you can prolong it as you want to, which is a very new idea. Now that leads me to Riemann, the last one I want to talk about here, who insists on using the Dirichlet concept of function, both in his dissertation on complex numbers and in his Habilitationsschrift on trigonometric series and the integral, Riemann integral. And he, well, let's not read the entire thing. He says that C is a variable quantity and so on, and it can vary in such a way. And then he says, clearly, this definition does not at all specify a law between the different values of the function, so that if the function is given on an interval, the manner of its continuation outside the interval is left entirely arbitrary. So it's exactly this that we did here, that Dirichlet did here. That's what he points out is important about this. So we've seen this in connection with complex functions. He also adds that the function should be complex differentiable or satisfy the Cauchy-Riemann equations, but he also in that case makes it clear that we require in that where he says where a function is considered independent of its expression, even in this paper. So there's no expression necessarily, but we have the Cauchy-Riemann equations. He clearly thought that this generality of the new concept of function was essential to his new mathematics. And let me just also point out how it gave him an easy way of extending the integral. As we probably most of us know, the Cauchy had already replaced the Eulerian idea of an integral as being an antiderivative and replaced it with a definition that says if you have a continuous function and then you look at an interval from x0 to x, divide it up and look at the function's left sum, so to speak, is this sum here. Then you can prove that when the distance or the width of these intervals go to 0, then this will converge towards a constant, and he calls it the integral. So here Cauchy has defined the integral of a continuous function. We usually call this integral the Riemann integral, and the reason is that Riemann says, no, let's not from the start assume that f is continuous. Let's just say f is a function, then we make these left sums or mean sums as he does, but that doesn't really change anything. And use it for all, and then we can see, does the mean sums, do they converge or do they not converge? And if they converge, well, then the function has an integral. If it doesn't, then it doesn't have an integral. And he shows that there are actually many discontinuous functions that are integrable in this way and not integrable by the Cauchy in the Cauchy way. And for example, he has a very famous example of a function which is has infinitely many discontinuity points and is still integrable. So in that way, you can see by starting out with the completely general Dirichlet concept of function, without just limiting himself down to the continuous ones, he has made a huge generalization of the integral concept. So he has almost got it for free, this generalization, but just by looking at the general concept of function. So now I'm not going to go any further. Now we have reached sort of the end of the 19th century, where the Dirichlet concept of function became the accepted general concept of function. Except there were, of course, people like we have seen Brill-Noether and Weierstrass who were not so happy about it. But people had sort of accepted that we should begin with such a wide definition of functions. And of course, Brill-Noether and Weierstrass are right. One cannot conclude much of interest about general functions. So this Eulerian dream, and perhaps even Cauchy dream, that there would be a part of analysis which could be described for all functions if you just limit the function concept to be something smaller. That had to be given up. There is no one way of limiting the function concept so that analysis will work in this subset in general. So one had to accept that each domain of mathematics and even each theorem requires its own set of assumptions. You cannot say, like Euler, for example, he would just say, take a function, then you can differentiate with respect to x and y in any order, and you get the same thing. That would he say. Well, we of course know, well, we have to make suppositions. We can't just take any function and then differentiate it. Well, we have to make assumptions. It has to be differentiable and blah, blah, blah. And that's, of course, what we have to live with nowadays, and what, in a certain sense, makes analysis so hard to teach. That is, we have all these assumptions that always come before the really important part of the theorem. Okay, so the conclusion here is that Brill-Noether, as far as I can see, gives a very detailed and critical comparative historical analysis of the various approaches to algebraic functions and curves. And they include some reflections on the development of the general concept of functions. And they touch on some of the important changes made, but often in a somewhat sporadic way. They don't really go into detail with it. And they don't dive into the most important changes that I think are primarily important for the understanding of the history of the function concept. In particular, what causes the changes and what was the nature of the changes. And in particular, I think that the courses from physics are undervalued in their presentation. But it's still an impressive piece of work they've done. So that's it.
Thank you. We have time for some questions. Yes, Hans?
May I come back on the question about Dirichlet's concept, and you showed us the proof of this theorem with the integral and so on. I didn't really get why he introduced it. He could have proved this theorem for a more restricted kind of concept of function as well with the same strategy.
No. I mean, if you insist that analytic expressions are what we are talking about, then you cannot just take a function and then continue it in any way you want.
Yeah, okay, but the case one, what about case one?
Yeah, he could have done that for algebraic functions. It works for any function as long as the function is piecewise continuous and piecewise monotonous. That's what he needs for the proof. These are, and that's also different from many of the earlier assumptions you have made, that they have been sort of ad hoc. You just say, now let's talk about analytic expressions. But it's not because you want to prove a particular theorem. That also is shown in the discussion between d'Alembert and Euler, where d'Alembert, in fact, as we would say, argues for the fact that these Euler discontinuous functions are not even differentiable, and therefore you cannot say that they satisfy the wave equation. But that's not how d'Alembert phrases it. He phrases it in a somewhat strange way, and that's because they think of that it's either an analytic expression or it's not. But that division is simply not relevant for the discussion of whether it satisfies the wave equation or not. I mean, there are many analytic expressions that are not twice differentiable either. So that's not, I mean, and I think also Dirichlet wanted to do this, first of all, because, I mean, he had learned from Fourier that it has to deal with all functions, but also because if you want to describe physically what's going on in a domain, how the heat is transferred and so on, well, it's artificial to say that it should be only described by an analytic expression. Why should it? I mean, there's no particular reason for that. And also in the case of for example, Riemann's, when he wants to use the Dirichlet concept, the Dirichlet principle, he wants to minimize a certain integral. But who says, I mean, it's even more strange to say that the minimizing function must be an analytic expression. Why should it be? There's no reason to assume that. Well, I mean, that's already a question that Weierstrass pointed out, that we don't know that it is a minimizing function. But asking that it should be analytic in this way of analytic expression is even more strange. Why should you assume that? Yeah.
Yes, thank you, Jesper, for this crystal clear presentation. Very interesting. My question is about was I think not this slide, but when you spoke about the fact that at the end of the 19th century, mathematicians gave up the earlier dream of a finding of subset functions, where most interesting analysis in algebraic function theory led out. The question is it a statement you deduce from the lecture, the reading of Brill-Noether?
No.
Or
No.
is something Brill-Noether themselves state?
No, Brill-Noether doesn't state this. No,
yes.
no, that's my own.
It's your
My own conclusion. Yes, that's my own conclusion. Yes, yes, and I think it's quite important also because I also refer to Cauchy as you of course know. I mean, in Cauchy you have this idea that if you don't read Cauchy very carefully, you will sort of get the idea that almost everything in analysis goes well for the continuous functions. I mean, in Cauchy, you'll find many places where he just, even in the courte analyse, just says let f be a continuous function. And then he goes on, and then suddenly that's in the differential calculus. Then he finds its derivative and so on. So he sort of implies more or less that all functions can be differentiated, and he shows that all functions can be integrated, all continuous functions can be integrated. So it's as though he has this idea that if we narrow the concept of function down to the continuous ones, we have sort of a rigorous domain in which we can work. Yeah.
And a funny remark, an observation about Cauchy's picture,
yeah,
photography. But you know, Arbogast died early 19th century, and photography was invented in 1839. So no, it's not the picture of Arbogast.
But is this a photograph? Well, maybe it is. I was actually very surprised when I found this picture. I thought that there would not be a picture of this person that nobody has heard about.
Absolutely impossible.
Okay.
Good question, Karin, and one by.
Thank you. My question is, how did the understanding of functions concepts differ between the 18th and the 19th century?
Yeah, I mean that is the difference is that in the 18th century with Euler, functions had to be expressed in one analytic expression. So it has to be a formula involving, and I didn't go into that, but plus minus division, multiplication, extraction of nth roots, taking of logarithms, exponentials, sines and cosines. You can even perhaps allow integral signs. You can certainly allow summation signs, infinite summations, and so on. I mean, everything you can think of as something you can write down with some analytic notation is allowed by Euler, I think. And then when we come to the Dirichlet concept of function, it's just a question of whether for each x there is a y. There is one y in most cases, unless, I mean, they're not entirely consistent, whether you only need to have one y or you can allow multiple valued functions. I mean, in complex function theory, you often do that if you don't introduce the Riemann surface. No.
I have a question, yes. Could you go back to the slide which you discuss the roots of the concept of function, the prehistory, what they call the prehistory of the concept of function. Because somehow you said, I would have expected, like in fact, Yushkevich, one might think of, and you suggest several things.
Yeah.
Yes.
Yeah.
However, okay, and this is also what basically Yushkevich says when at the beginning of his paper on the history of the notion of function.
Yeah.
My first remark is that I'm not sure Mesopotamian tables of multiplication or reciprocals
I thought of that.
had been published at the time. I mean, it was only 1 or 2 decades earlier that Mesopotamian documents started to be published, and I don't know about these tables, whether they had been published in 1894. I don't know.
That's true, but that's also why I especially pointed to this thing, because that they knew about.
All of a sudden, I'm struck by the fact that, and this goes back to Yushkevich, to consider a table of chords as it stands, as a function, starts from a very modern notion of function.
Oh, yeah.
That you have a set and a second set, because what is striking in the fact that they choose rather Apollonius is that they choose something where there is a notion of discontinuous variable. So
Yeah.
somehow there is, in the concept of function, the variable that took all the values was absolutely central, and somehow they are still in this world where functions depend on an independent continuous variable.
Yeah.
And so I think that these thoughts that we may have depend on a very modern notion of function.
Yeah, I mean, it depends on, because I think the idea of the lawful dependence of a quantity upon another, that is true. I mean, they talk about a quantity, and that sort of suggests that it might be a continuous quantity. That is true. So yeah, I completely.
So it's very interesting. You refer to a change in the 20th century in the notion of function as something that each element of X associates an element of Y. But this somehow is embedded in our imagination of the roots.
Yeah, except, I mean, when you look at the chord table here, of course, Ptolemy and everybody who read this chord table will know that you can interpolate in it, and for that reason it is, in a certain sense, a continuous variable. I mean, but you have just made the table for a finite number. I mean, there's even this part here where you interpolate.
So it's the chord that may be considered a function of the angle, but not the table.
Yeah, that can be true. Yeah, you're right. But I think but I mean, this continuous variable and so on, the fact is it's much more obvious to see that in the definition of, for example, the Archimedean spiral or the quadratrix, where it's definitely, you have this idea of a motion and so on, but they don't mention that either, which I think is.
I think that we go the other way around. Namely, if for them Apollonius stands out, this should tell us something about their concepts and the way in which their mathematical culture has an impact on their history.
Yeah.
And this is something which is very interesting to think about, how the history we are writing depends on our mathematical culture.
I think that's also what I wanted to say.
Absolutely.
But you say it more clearly.
No, but I wanted to emphasize this point.
Yes, David.
I wondered what role does this religion and the existence of God play in all this argumentation?
The what?
The existence of God.
Of God?
Because you didn't talk about this, but I read texts of Cauchy where he argumented, for example, this is not for functions, but for infinity, where he referred to God to show that eternity contradicts the idea of infinity. And I wondered if this kind of argumentation appears in the texts of Cauchy or Dirichlet or Euler, and maybe Brill-Noether this too, to argument for this concept to develop.
Well, that sounds very interesting. I haven't found any reference like that, I must say. As far as I remember, even in the introduction, in the Cours d'Analyse, Cauchy doesn't talk about God. I think. No, okay. No, I mean, I know from reading Brill-Noether, I mean, Cauchy thought that he had to be just as rigorous in his mathematics as he was in his religious beliefs. So in that sense, I mean, what usually you think that's strange that we have this very, very conservative mathematician who revolutionized mathematics completely. But for him, there was no contradiction. I mean, he was just rigorous in both areas, in his opinion. But I don't know if, I don't think I remember having seen any mention of this. No. And in connection with, for example, the infinitesimals, I mean, it's true Cauchy uses infinitesimals, but they are redefined as, in a certain sense, variables tending to zero. But at least he says, a variable tending to 0 becomes infinitely small. But in certain of his proofs, he actually says that an infinitely small quantity is a variable that tends to 0. And I haven't seen any reference to God there either. But he does redefine it in such a way that it has something to do with the limits concept.
I mean, when I said that, I mean, Euler was very religious in the Protestant sense, and he alludes to religion as soon as he gets to a domain that cannot be treated by a number. As long as it's nice, it's okay. But if you try to use it to analyze human vision, the legislature,
Yeah. Well,
okay, so we are out of time, but we can catch just the last question by or during the break.
I can.
So thanks again to Jesper.